So hi, my name is Randall Hunt. I have 25 minutes. I'm going to go very, very quickly. This talk is an unabashed advertisement for AWS, but I am not a salesperson, and if you end up using more AWS because of this, that's totally fine. And if you completely never touch AWS, that's also fine with me. The research that I'm presenting today wasn't done by me. I'm not that smart. I have taken it quite a bit further than the original research, but then Google went even further than me and published a bunch of papers about it. So this is now 1 year out of date. I'm going to talk a little bit more about it. So this is me. That's my official badge photo. They asked me if I wanted it retaken, and I was like, no, it's perfect. I have started out programming in video games, and then I studied physics, and I worked at NASA for a while, and then I found out that physicists don't make any money, so I went on LinkedIn, and I changed my title to software engineer and tripled my salary overnight. I worked at this small company called MongoDB. I saw it grow from 10 people into like 600 people. It was a very fun experience, and then I went to SpaceX, and now I'm at Amazon Web Services. It's fun. I think Python and C++ and all those good things are great. I think JavaScript is essentially a mass psychosis. I say that with a lot of endearment, but if you can't avoid JavaScript, do. Please follow me on Twitter. Okay, so what are we talking about today? I built this bot called WhereML, and what WhereML does is you post a picture, and it will guess where in the world that picture was taken. So it does not use the EXIF data, it only uses the pixels in the image. It's fairly accurate. So if you want to try it, you can hold up your phone to the screen right now. It should pop up a QR code, and you can go and you can post a picture. This is what the experience looks like. It's like, hey, WhereML, where was this picture taken? I should probably get my driver's license out of that. And this is a picture of Seattle, and so it's going to post, and then Twitter's API is going to take a second, and it'll say, with the Google Maps static API image, like, hey, it's in Seattle. And it works really well. So pretty much anywhere in the world that we have data for, we can build a cell out, and we can say, these are the features that we want to identify. Google's done a lot of really cool research since this was done. And I'll talk more about that later. The architecture looks like this. Twitter has something called the Account Activity API. If you Google my name, like the first thing that comes up are all of my rants about how bad this API is. That said, they have listened to the feedback and iterated, and I think it's finally into a place that I would call production. They said it was production 1 year ago, but they were incorrect. This API calls out to an Amazon API gateway, which is essentially like a giant reverse proxy service. That calls out to an AWS Lambda function, which is just a piece of code that runs in response to some event. In this case, that event is a web request. That event goes and talks to Amazon SageMaker. You can tell it's an Amazon product because we put our name in front of it. What that does is it's essentially a Docker container that's running MXNet, which is a popular machine learning library. And that is running the model that we trained. So I'm going to talk more about that later. First of all, why is AI important? I think we covered that in other sessions. This is a really cool video. Has anybody read 7 Eves by Neil Stephenson? So it's a really great book. If you take nothing else away from this presentation, go read that book. It's really excellent, especially if you like sci-fi. Within 7 Eves, there's something called Perambulator. So when I worked at SpaceX, one of the first things that we were trying to solve was like, how do you have lots and lots of satellites in orbit, and how do you make sure they don't run into each other? And we built this thing called Perambulator, and we stole the name from 7 Eves. And what it does is it orchestrates the different environments and the different satellites and stops them from not really colliding with each other, because space is really big and the satellites are really small, but stops them from interfering with each other and making all these adjustments. So this is the Kiva robotic system, now called Amazon Robotic System, that runs in our fulfillment centers. I was coming by the airport and I saw one around here. Pretty cool stuff. This is a drone, that's terrifying. This is a store where you walk in and you steal a bunch of stuff, and this is applying AI. What it does is it has cameras in the ceiling, it has RFID on the product, so as you pick something up and as you have the camera in the ceiling, what it's doing is it's identifying, okay, subject X walked in, subject X picked up the object, left with it. Here you'll see this lady is about to make the worst mistake ever. 1 second. It involves a cupcake. Go faster. Basically, she picks up a cupcake and then she puts it back. You should never put a cupcake back. Let's just be real with each other. Cupcakes always, commit to it. So our mission with machine learning at Amazon Web Services is actually to put it into the hands of as many people as possible. And if you don't believe me, there's a really, really cool result in Nature magazine a couple months ago that talked about how a hobbyist was able to find and solve a graph theory problem that had existed for like 500 years. And that's what we want to do, is we want to bring a diversity of perspectives to bear on every single problem in the machine learning space. So you want to take the tools that were previously locked in these ivory towers and these Fortune 10 companies with billion-dollar R&D budgets, and you want to put those tools into the hands of as many developers as possible. In his or her dorm room, in their office, in their garage or basement, like wherever you are, we want to make sure you have these tools available to you. And the way we do that is we have lots and lots of customers. We split things into like frameworks and infrastructure on the bottom level, services at this medium level. I would say very few people actually spend any time in that frameworks and infrastructure space. Most of the people are hanging out in this middle tier or in this top tier. This top tier are API-driven AI services. I'm not going to talk about those today. What we're really going to talk about today is this middle tier and a little bit of this infrastructure tier. I should fix the E on my slide. I have been told that by Amazon PR and legal that I need to stop saying I have a favorite service, because we have 170 services and I'm supposed to be equally in love with all of them, but I'm not. Like, SageMaker is by far one of my favorite services. It's one of the few things that we've built that is not like crazy, let me do everything within AWS. It's an orthogonal piece of software where you can pick and choose the parts you need. It has a really robust open source Python SDK. But let's talk about ML. Everybody gets how ML works. Everybody's seen this before, MNIST, right? This is the MNIST data set. This is a series of 30,000 or so digits, grayscale values, 28 pixels by 28 pixels. These are animations by Grant Sanderson. These are not by us, but we're very pleased to sponsor his YouTube channel. It's called 3 Blue 1 Brown. If you want a PhD, if you want to know more than a PhD in machine learning, go look at his YouTube channel. So what we're doing is we're taking those 28 pixel by 28 pixel images and we're splitting that into one flat array of 784 pixels. We're going to create one layer here. This is going to be our first hidden layer, and we're going to connect it to every single layer in the input. We're going to do the next thing. We're going to connect it to every single layer in that next layer. Go faster. I only have 25 minutes. Go, go, go. And then we're going to do this last layer, which is going to be the digits 0 through 9. And the act of training is essentially just going and figuring out what the right values are for all of these edges. And this emulates kind of the human visual cortex in a way. So, well, we used to think it emulated the human visual cortex, and then we got really, really fancy MRI machines, and we found out we were totally wrong. But like, if you look at the old model, what happens is, there's light coming from the ceiling, and then there, photons and things coming and resolving, hitting my optic nerve, going through the lens and the retina, and that's coalescing into like imagery in my brain. Like, weird conscious human meat thing is going and saying, okay, this is an image, this is an audience, they're super bored, talk faster. And the way that we train that is the same way that we train a human, like a human baby, right? Like, how does a human baby learn to like recognize numbers or letters? You show them a bunch of data, and then you tell them, no, dummy, like it's this one. And that's how humanity persists, which is kind of weird. We're all just like this weird compression algorithm for information, a very, very slow organic compression algorithm. But that's essentially what machine learning is it's a compression algorithm for experience and a compression algorithm for intuition. So we're taking that and we're applying it to these really boring problems like identifying digits, but we're also applying it to problems like self-driving cars and identifying breast cancer early and things like that. So a neuron is not a thing that holds a number. A neuron is a function. And what I mean by that is a neuron has as inputs all of the other nodes that it's connected to, and as outputs all of the other nodes it's connected to. You do not have to have fully connected layers. You can have all kinds of complex layers in your network. This is a very simple network. I'm going to show you a much more complex one in a little bit. Also, I'm recovering from like the worst bout of food poisoning in my life. So if I like faint or something, just hook me up to an IV. I lost 10 pounds in 3 days. So you might think like that the network is going and saying, okay, well, if I want to identify via successive layers of abstraction what a number 9 is, then I know that this loopity-loop or first I'll do edge detection, right? Like, I could apply a convolutional filter over the image. Okay, cool, that makes sense. I know how to do that. I'm a great programmer. I can use pandas. I can use NumPy. I can do all this stuff. Or you could say, oh, let me just figure out where the edges are, and that'll be my first layer. And then my second layer is going to be, okay, if I have a loopity-loop and a line, that corresponds to a number 9. And your intuition might lead you to believe the network is doing this. And the answer is sometimes that is what the network is doing. Sometimes it's not. And as you get deeper and deeper into these networks, it becomes much harder to visualize what's happening at each layer. Google's done a lot of really cool research on that lately. Okay, so how does this business work? First, you have some C-level exec who goes to some conference and hears about machine learning and decides that this is what the entire team needs to focus on for the next 6 months. They allocate like 100 grand and 2 interns to the project, and they say, hey, we have all this data, let us throw the 2 interns at the data, and they can do whatever they need to do. And then you don't actually have any a goal or project in mind, but imagine that you did, like you set out with a clear purpose. Wouldn't that be great if that ever happened in real life? So then you get into this section, which is the data preparation and cleaning. That's very important. The most important step by far, I don't know where, the most important step by far is visualization and analysis. This is the least, like people do not get, okay, if I showed you a set of 13,000 numbers and I asked you to find me the outliers in that set of 13,000 numbers, who would be able to do that right now? Just like you could scroll through, you could tell me what all the outliers are. Now, if I plot those numbers on a line, can you now tell me where the outliers are? So visualization is so vital, and a skilled data scientist is somebody who can really take complex pieces of data and help you visualize them and help you identify which sections you need to apply attention to. Lots of funny stories on that I don't have time to get into. Then you go into feature engineering and training and tuning. This section of like training, parameter tuning, and evaluation, this is basically entirely automated at this point. Whether you're using TensorFlow or PyTorch or Chainer or MXNet, doesn't matter. Even the hyperparameter tuning part, like you can use naive Bayesian optimization and you can just say like, hey, I want to blindly swipe my credit card until I get the right result. Cloud. So then are the business goals met? And of course, no, they're not. So you repeat this process ad nauseum, you repeat this process until they are actually met. And eventually you come out with this model that you're going to deploy into production, and people spend a lot of time talking about and focusing on all of this part. This is surprisingly not where most of the costs are. Most of the costs are in this inference section. And deploying machine learning models is quite different from deploying traditional applications, or I would say it's a superset of deploying traditional applications, because you still have to monitor memory limits, logs, CPU, all this other good stuff. But on top of that, you also have to measure whether or not the inferences you're making are correct. You have to have some feedback mechanism that says, is this model doing the right thing? And if you don't, try using autocorrect on your phone. So then you go and you make these predictions, you do this monitoring, and then you go into this retraining step. So all good fun. So how do you formulate these questions? Domain knowledge and expertise, or in the cynical, jaded world that I live in, some executive who went to some conference and decided this is the most important thing now. Then you have lots of different tools to help with this. We have the AWS Glue data catalog, which kind of accumulates things from S3, things from Redshift, Hadoop clusters, all that good stuff. And then you go into this section where you're visualizing. This is generally done in a Jupyter notebook, let's be honest. Maybe there are tools out there, companies like Pachyderm, or there are probably 30 different tools out there that people use. Use whatever fits your pipeline best. Don't like worry too much about what you're using here, because it's gonna run on some developer's desktop more than it's gonna run in the cloud. Then you get into the deployment part, and this is where you got like big money being spent and you really need to focus on things. One of the things that you can do here is a lot of the times the models that you train are not necessarily the most efficient models to deploy. You can prune those models. You can prune things out of them and make them a little more efficient and a little better. And you can even optimize them for specific hardware subsets. So if the AVX512 instruction set exists on some of your platforms but not on others, you can go and make different versions of the model that are optimized for those things. Or if you have models at the edge, you can optimize for those edge devices. So SageMaker does all of this, and it's wonderful, and I love it. And Amazon Legal and PR tell me that I need to stop saying I have a favorite, but this is my favorite. Don't tell them. Okay, so what does it do? It's like notebook instances on the one side, it's built-in algorithms on another side, and then custom algorithms and hosting and all kinds of other good stuff. But since I only have 25 minutes, we're going to skip over a lot of this infinitely scalable built-in algorithm stuff. and we're going to talk more about the managed training service. So the managed training service says, I have a bunch of data that exists in an S3 bucket or some other location. I would like for you to go and run lots of different versions of this training job for me, figure out the best hyperparameters, and then figure out also which one is converging quickly, and save all the models that weren't converging quickly just in case I find out that I was stuck in some valley and I can go back to them and start again. And then I want you to generate that model, throw it into S3, and then I want you to create a Docker container that will deploy that to me in an deploy that for me in an auto-scaling environment that I can run and serve inferences for. The gross majority of the customers that I work with are just doing ads, and that's a really boring use case. I did, however, get the chance to work with a customer that was doing breast cancer prediction, and that was a very cool use case. There's another very cool use case recently, which was, has anybody used C-SPAN? For those of you who may not be from the United States, it's an American entertainment network. What happens is, it's very, very funny. It's the US government 24/7 with like some camera pointed at someone, and they are saying something that really isn't going to do anything for anybody anytime soon. But what happens is that there are lots and lots of different people speaking all the time on C-SPAN, and you want to be able to go and ignore all the really boring stuff that doesn't matter, like here, 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 order, order, or whatever it is they say, and you want to skip past that, and you want to skip to the substance of what they were saying when that happens. And what you do is you say, okay, well, I'm going to transcribe all the audio, I'm going to transcribe all the video, and then I'm going to throw the identified people into Elasticsearch so that I can go and sync to any particular timestamp. And that was another really cool use case that we got to use. Okay, so yeah, all of this is fully managed and secured, and it has resource level permission. So if you don't want to give people access to the underlying data for some particular reason, like you've got to be safe, like maybe it's healthcare data, it's got PI, or it's got personally identifiable information inside of it, then you can do that, you can lock that data down, and you can only share like the model with them. Okay, so yeah, you deploy it, you can deploy multiple versions, you can A/B test those, and you can get lots of different other good things going on. And it works with MXNet, TensorFlow, Chainer, PyTorch, Caffe, like Keras, you know, all the frameworks that you're used to hearing about. That you can deploy those scripts with no changes. You just say, like, hey, the data's here. Look in /opt/data for the data. Look in /opt/output for the output. Good stuff, right? We have lots and lots of different open data sets. If you are interested in hosting another open data set on AWS, we have a program for public data sets where if it's like for the good of humanity, which is a completely subjective thing that we will decide, basically climate research or Alzheimer's research or I don't know, whatever bad things that we want to solve, we will host that data for free, and we will make sure other people can go and use it for free. To some extent. We'll do the hosting for free, but the going and using it for free, like if you're going to download 16 exabytes every day for 10 years, maybe not. This is really, really cool. You can add in your own data sets. Even if they're not hosted on AWS, you can throw them up there. You can create your own labeled data sets. So we have something called SageMaker Ground Truth, which is very similar to like annotating data with an army of interns. You can either use your own army of interns or you can use our army of interns. And you can go out and do like image segmentation, it can do classification, it can do labeling, object detection, all those good things. And as those interns go and label the data, and when I say interns, I mostly mean people like me who have insomnia, you can go and you can train an active classifier. Great. Lots and lots of really, really cool data sets here. I think this 35 terabyte data set from the Brain Science at UW Institute is really cool because it has different labels about different things that were wrong with the brains that they were scanning. One of the interesting things about humans is we don't have lots of good examples of good brains. We mostly have examples of brains that are broken in these data sets. So it's kind of fun to like find, that's actually one of the benefits of the healthcare system in America is that we're like very, very cautious, so the doctors always send you for an MRI, even if you might not necessarily need one. So occasionally we do get good brains, whereas if it were only when you were super sick, we would not have any of that data. So the one data set that we're talking about today is the Multimedia Commons data set. This is a set of images collected from Flickr over the course of several years, and thanks if anybody uploaded something Flickr and put it in Creative Commons. So the model that we're talking about is LocationNet. It's actually based on research that was done at Google called Planet by Wayland et al., who I think lives in Los Angeles near me. There was also, way back in like 2005, I know way back, there was some research done at Microsoft on this project called Snapdragon. Does anybody remember that? It like merged photos together. So that was really cool. That was the first time they really started saying, hey, we could figure out where in the scene this photo belongs. And then it stalled because it turns out it's really hard to do. But we've gotten much better at it now. And then this paper came out, and this was the first approach of deep learning for geolocating images that had been proposed in a while. And then LocationNet came along, and this was, hey, what if we pre-process the data? And I'll tell you more about that now. So what we do is we take 33.9 million geotagged images, we subtract out all the images that are like just one color, like one color blue, one color red, one color black. Like we just take all those images out because they're low value, we don't need them. We do that during our visualization step where we plot the mean pixel value. And then we take all of those and we get the EXIF data from them. So we get the latitude and longitude coordinates that are on those machines. And then what we do is we subtract out all the 0, 0 longitudes because that's in the middle of the ocean, nobody is actually there. And we create a structure using Google's S2 spherical geometry library. I will demonstrate what that looks like in just a moment. But those 15,527 multiscale geographic cells are how we're going to make our predictions and our classifications about where an image is. And then we train for a couple days. This was the original research. So the training and processing time is now down to like 30, 40 minutes for me. So we were able to make significant improvements in the code. I say this in the nicest possible way because I used to be one, but academics are not always incentivized to write the most performant code. So we can make a couple changes and a couple improvements that where perfect is the enemy of good, is I think what you said earlier. So it's built on top of ResNet 101. ResNet, if you've never heard of it before, is a residual network. It's basically, what happens is it adds a cheat code in. So as you add more and more layers into a deep learning network, you hit this issue of, hey, like, I am having trouble propagating the data backwards and making sure like the network is learning and converging quickly enough. So ResNet basically puts in cheat codes that say, hey, let's just propagate larger and larger matrices of the data down so that we don't have to propagate as far backwards. This is what it looks like. I'm sure I don't have to explain any of this. It makes perfect sense, right? Straightforward, super, super good network. This is what the multi-scale geographical cells look like. So if we look at a city like London where we have lots and lots of data, we can actually split that and subdivide that into many, many sections. And then we use this really cool thing called a Hilbert curve to preserve locality across the X and Y coordinate plane. So the more curves you add in the Hilbert curve, the more close the points on a number line are in a X and Y coordinate plane. I almost got a tattoo of this, but then I sobered up. You can do really, really fast inferences. So this whole model is like 300 megabytes. So it outperforms the 40 gigabyte DenseNet model that Google trained by about 20 to somewhere between 2x and 20%, depending on like what the terrain is. It's got really, really excellent features for identifying like the Eiffel Tower versus the Las Vegas Tower, or any kind of unique landmark. It can do very, very well on. It can tell you not just like where that picture was taken, what city, but it will tell you which side of the street you were standing on when you took it. Now, for 7-Eleven signs, it has no idea. I think 7-Eleven must ship the exact same light bulbs and the exact same font and the exact same everything to every store that they have because it just really has no idea. So one of the things that Google did to improve this was they created a like LSTM model. So that's a long-term short-term memory. And they're like, first of all, if we have lots and lots of points in one location and these have a high enough confidence value, maybe we shouldn't be serving, one location was in Nepal and one location was in South Africa. Like maybe these things are different. And that's an improvement that I would like to make in my model, but I don't get paid to work on it, so I haven't. True story. So these are just some interesting pieces of information. This was trained on fewer images, took less time to train, and outperformed the other models significantly. And it just shows like data pre-processing can save you a lot of time and effort. all kinds of other good stuff here. So much better performance in many cases on predicting within 1 kilometer. And then what does the infrastructure look like? I'll go very quickly. This is API gateway. So you have a request coming in from Twitter. You verify it. You make sure it's all good. You check the secrets, all that other good stuff. I'll make these slides available because I don't have a lot of time, sorry. This is where the fun stuff happens. This is where you go out to SageMaker. SageMaker, it's loading the model, and then we're loading the grids. So when I say load grids section, that's really just loading in that section of stuff. And then we go, and this is the most important slide in the entire presentation. If you take nothing else away from this presentation aside from reading the book 7 Eves, take this. If you add this offset to any country code, it will give you the emoji flag for that country. Yeah, dope, right? Really bizarre. That is like a feature of Unicode. All right, so then you go, you do the prediction. The way you do the prediction is you make a very simple Flask app. You return an empty 200 OK as part of the health check. And then you expose it on port 8080, you load all your stuff in, and then Twitter is frustrating. All of this was built live on twitch.tv/AWS. So I'm on twitch.tv/AWS. I started the channel in 2016. We have 8 million viewers now, and it's just live coding. Thankfully, I don't have to do it anymore, and we have a budget now. Whereas it started, it was in my room, and we had no budget, and you heard me swear a lot. I'm not allowed to do that anymore. I would say check it out. We build stuff like this live, so you can see us yelling at our computers and trying to remain sane. Thank you so much for your time. I really appreciate you coming out. That's it.